Hi, everyone, and welcome. It's my honor to introduce our work, Full-DoF Egomotion Estimation for Event Cameras Using Geometric Solvers. This paper is a collaborative effort by Ji Zhao, Banglei Guan and Zibin Liu from the National University of Defense Technology, and Laurent Miep from the Mobile Perception Lab at Shanghai Tech University. Our code is publicly available, and you can find the link on this slide. So, let's start with a quick refresher. What are event cameras? Unlike traditional frame-based cameras, event cameras capture pixel-wise intensity changes asynchronously, generating a stream of events. The advantages are significant. They offer extremely high dynamic range, very low latency, and critically, no motion blur, making them extremely well-suited for high-speed robotics and challenging lighting conditions. Our primary motivation is to achieve pure visual 6-degree of freedom motion estimation using only events. However, this presents a significant geometric challenge, especially when addressing the full motion model, which includes both rotation and translation. We aim to develop novel event geometry based on normal flow. While there has been excellent work, such as by Peng et al. And Gao et al., many existing geometric solvers for event cameras, as highlighted here, do not directly estimate the full 6-DoF, particularly the angular velocity. This is a key gap we address. Our work makes several key contributions. First, in terms of geometry, we introduce a novel coplanarity relation for the Eventale manifold, which leads to a more reliable Egomotion estimation solution. Second, we propose several sparse geometric solvers specifically formulated for Full-DoF motion estimation parameters. Third, for optimization, we leverage the atom optimization framework to efficiently address the resulting complex optimization problems. And finally, we provide a theoretical analysis of pure rotation cases, an aspect that has not been deeply explored in the context of geometric solvers for event cameras. Let's dive into our Egomotion estimation methods. We start with the incidence relation, building upon prior work by Gao et al. This equation describes the relationship between an event and its corresponding line in the image plane, incorporating both angular velocity omega and translation. Our line incidence method uses batches of these incidence related to directly estimate angular velocity. For translation estimation, we again utilize the incidence relation. As you can see from the equations, by relating the event line to the scene line, we can formulate constraints that allow us to linearly solve for the line velocity, which is directly related to the camera's translation. A core novel aspect of our work is the coplanarity relation. Here, we consider the normal vectors derived from events. The key insight is that for a planar patch in the scene, these normal vectors observed over time must be coplanar. Our COPBAT method leverages this geometric constraint, using batches of normal vectors for robust rotation estimation. To solve the optimization problems derived from these geometric constraints, we employ the atom optimizer. We investigate different rotation parameterizations, including exact rotation, first-order approximations, and cascade of 2 rotation parameterizations. Table 1 here provides a concise comparison of our proposed solvers. It highlights in the underlying geometry, the type of observations used raw events versus normal flow, the variables being solved for, and the resulting matrix sizes, giving an idea of computational complexity. We conducted extensive simulations to validate our approaches. Figure 1 shows results on synthetic data. These plots demonstrate the relationship between estimation errors and various critical factors. As you can see, our methods show robust performance with an increasing number of events plots AB, varying numbers of lines plots CD, different noise levels plots EH, which is crucial for real-world applicability. Further in our simulations, Figure 4 illustrates the landscape of the objective functions for our solvers. Importantly, when more than 3 lines are included, these objective functions exhibit distinct global minima, which is highly desirable for robust and reliable optimization. The tables on this slide show the runtime and numerical stability of our solvers on noise synthetic data. They demonstrate that our methods are not only accurate but also computationally efficient and stable. To validate our methods beyond simulations, we conducted real-world experiments. Using standard angular and linear error metrics, our results, detailed here, show that the proposed solvers perform effectively on real-world event camera datasets. This underscores their practical viability for Egomotion estimation in real-world scenarios. In conclusion, we have presented novel solvers for event-based Egomotion. A method for full 6-DoF recovery without requiring auxiliary sensors. An approach that leverages event manifolds and novel coplanarity relations. And we have validated performance with efficient optimization on both synthetic and real-world data. Thank you very much for your attention.